Welcome back. In the previous lecture, we discussed about few theorems which relates uniform convergence and continuity. At the end, we have seen this result that if we have a sequence of continuous function which converges uniformly, then the limit of the uniform convergence is also continuous. But here, so we completed that proof, but the converse need not be true. Why? Initially, we have seen some motivating examples where we have seen that fn of x, which was defined like n square x upon 1 minus x square to the power n, where x can take any value in the interval 0 to 1 and n in the set of natural numbers. Here, if you see the limit of this convergence, pointwise convergence, is 0. Okay, here fn is a sequence of continuous functions. Okay, our f of x, which is 0, is also continuous, but this convergence is not uniform. That is, if a sequence of continuous functions converges pointwise to a continuous function, it need not imply that the convergence is uniform. Okay, now we shall see another theorem that states, suppose K is a compact set and we assume the following hypothesis, that fn of x is a sequence of continuous functions. Then fn converges pointwise to a continuous function f on k. Then fn of x is greater than or equals fn plus 1 of x for all x in k and n running from 1 to 3 etc. If this is the situation, then our fn converges to f uniformly on k. So this is just the converse part of the previous theorem, but it is not true for all the cases. It will be true only in the compact set where the sequence has to satisfy this monotonically decreasing property uniformly. That is, for every value of x in the set k, if it is monotonically decreasing, then the convergence will be uniform. So this is what we are about to prove in this theorem. So in order to prove this theorem, let us take Gn. We define another sequence Gn with the help of fn and f. So fn minus f. Okay. Since fn converges to f pointwise, Gn converges to 0 pointwise. Okay. And fn of x is greater than or equals fn plus 1 of x. This will not be altered when we add or subtract the same quantity. So which means that our Gn is greater than or equals Gn plus 1. Okay, Now to prove Fn converges to F uniformly, it is enough to prove our Gn converges to 0 uniformly on the given compact set K. Now, in order to achieve this, let us consider epsilon, which is given. Okay, we will pick some arbitrary epsilon. Now, to prove it is uniformly convergent, let us suppose that it is not uniformly convergent. Then, let Kn be the collection of all such x in K such that Gn of x is greater than or equals epsilon. Okay, here since Fn is continuous for every n and F is continuous, Gn is continuous, right? Okay, so we know that this epsilon comma infinite is a closed set. What is Gn inverse of this closed set epsilon comma infinite? This is nothing but our Kn, right? So that is Kn being an inverse of, that is inverse image of a closed set under what? Under Gn, which is a continuous map. Under a continuous map, we conclude that Kn is closed. Okay, but how did we define Kn? Kn is a subset of K, right? So now Kn being a closed subset of compact set, Kn has to be compact. Okay, now since Gn is greater than or equals Gn plus 1, we would be able to establish that Kn is contained in Kn plus 1. Okay, now let me fix some x in K. Since our Gn of x converges pointwise to 0, there exists n sufficiently, okay, there exists n naught sufficiently large such that x doesn't belong to K n naught. Because Gn of x converges to 0, that means when your n is becoming larger and larger, this set, this Kn will not have any point in it. Because we are choosing all such x in K such that Gn of x greater than or equals epsilon only. Since Gn is converging to 0, after a certain stage, this set has to be empty. Okay, this means x will not belong to intersection Kn, or in other words, Kn naught is empty for some n naught. But what is the scenario? We have this Kn is a compact set which is decreasing sequence of compact sets. Okay, so basically this is a contradiction. Hence, what should we have? We should have 0 less than or equals gn of x less than epsilon for all x in k and for all n bigger than or equals n. This is what? 0 less than or equals absolute of sorry, this is 0 less than or equals fn minus f less than epsilon for all this case. That is absolute of fn of x minus f of x is less than epsilon for all x in k and for all n bigger than or equals n. This proves thus fn of x converges uniformly to f of x on k. This completes the proof. So we just have derived the converse part of the previous theorem, that is a sequence of continuous functions will converge uniformly to a continuous function. That we have proved. Now we have proved the converse part of this. Here let us make a remark that compactness is essential. Suppose if the compactness is not here, what is going to happen? Let us see. Let us define fn of x to be 1 upon nx plus 1, where x can take any value in the interval 0, 1. So this is what we have. Okay. What is limit n approaches infinity fn of x? This would be 1. Okay, because x can be whatever a small value, it can get closer to 0 or it will be closer to, it can be any value in this interval, but it's never 0. If it is 0, then it will be 1. If it is 0, it will be equal to 1. In other cases and all, what will be there? So it will have the chance that this limit goes to 0. Okay, so the limit of the convergence is 0. So that is fn of x converges to 0 pointwise. Okay, now is it uniform convergent? Whether the convergence is uniform? Now let us see what is Mn. It is supremum x belong to 0, 1 absolute of fn of x minus f of x, that is supremum of x in 0, 1 such that absolute of 1 upon nx plus 1 minus 0. So the supremum value would be 1 upon 2 and that will be attained when x is 1 upon n. Mn does not converge to 0. Hence, the convergence is not uniform. And you would be able to see that all other conditions in the theorem is satisfied. That is, it is a sequence of continuous functions. It converges pointwise to a continuous function. And fn of x is greater than or equals fn plus 1 of x. All these three conditions are satisfied, but k is not compact. Therefore, we were able to see that the convergence was not uniform. Okay, thank you.